an understanding of the current state of formulation chemistry, where the science is more or less an art form in balancing not only the interactions occurring in solution, but also the capital and labor required to optimize and produce advanced applications. And one such application that I'm very much interested in is drug delivery. Um, it has become obvious to me that there's also a large industrial need to understand specific ion effects, as well as addressing the behavior that interfacially active solutes, such as alcohols, hydrophobes, and other water-soluble polymers, for example, affect the surfactant activity and ultimately affect the solution behavior. If you include all of the general industries and applications, the market as of 2019 is closing in around $500 billion gross annually speaking. However, the manufacturing and production of these formulations are increasingly becoming regulated, as seen in California with Prop 65, and then the growing VOC list produced by the California Air Resources Board. Many states have begun to adopt similar rules, as well as good manufacturing practices, and thus many of the formulations we use today are becoming constrained to only using certain materials. Unfortunately, for a formulator, there are only a general rules of thumb to address how these solutes will behave in solution. And however, since there is such a lack of systematic studies, there continues to be a large opportunity for important research. The chemical logic for the colligative approach stems largely from William Ostwald's lecture on the properties of solutions that he gave in the 19th century. He stated that all solution properties may be categorized as either being a colligative, additive, or constitutive property by nature. And thus, you can look at this as a top-down approach, which at first is colligative properties, or solution properties that apply to all solutes that are involved in a solution, and that also includes polymers. And simply speaking, colligative properties of a solution is merely just a function of the solute's concentration and the temperature of the solution. In general, colligative properties are deemed to be independent of the nature of the solute particles. However, Ostwald and his assistant Breckman found that solute properties and how they affect the solution largely are dependent on the molecular composition, in which they deemed these properties to be additive. Madame Curie responded to this, in which she saw a similar behavior in which she called the solute's atomic core character. Further, you can go even further, in which the structural effects come into play, which she deemed the constitutive properties, which are a function of the arrangement of the solute. A great example of this is rheological properties that stem from solute positions as well as the interactions. Ultimately, Ostwald considered the non-ideality of solutions to arrive from the additive properties of the solutes, where the intermolecular forces occurring between the solute and the solvent are dependent on the solute's nature. And as such, we developed our colligative approach that essentially states that the behavior of a surfactant solute solution can be predicted simply by utilizing the solute concentration when the solute's additive properties are normalized. The colligative approach was somewhat inspired, but more or less provided more evidence to the work done by Andreas Zavitsas, who is a senior professor of chemistry and biochemistry at Long Island University, Brooklyn. Zavitsas produced a simple activity model of water using what he calls the Hydrophilic Number, or the number of waters strongly bound to an ion or a solute in solution that return a non-ideal solution to ideal. And this is in regards to Raoult's law and follows colligative methods such as freezing point depression. I have listed out the equations for Raoult's ideal molar chemical activity of water, as well as the activity of water equations. It should be noted that the activity of water is a very important quantity for food science, and if you enjoy any type of jellies or jams, this is one of the reasons why, one of the quantities why you don't have bacteria growing in them. Zavitsas showed that the hydrodynamic number, and that's pointed out by the arrow, can be utilized along with the freezing point depression that's above it and as well as the cryoscopic function to find the number of strongly bound waters to each mole of solute in solution, which in this sense the hydrodynamic number is a quantity of thermodynamic hydration in order to return this solution, a non-ideal solution, to Raoult's law or ideal. Using this method, we don't assume complete dissociation away from infinite dilution, and largely the hydrodynamic numbers are only valid up to specific molar amounts, and usually higher concentrations it seems to fall out. This can be observed though qualitatively if you have a freezing point depression curve, and I'll show this a little later. But you can qualitatively figure out at which the dissociation becomes a problem. The Hydrophilic Lipophilic Deviation, or HLD in short, is an empirical colligative thermodynamic model that describes the amphiphilic behavior of surfactants and other interfacially active solutes. Now on the left I have the two equations for ionic and non-ionic surfactants and their general forms. I have bolded the term that we'll talk about more specifically, and that's the function of alcohol term, and show how the colligative properties can be used to model this well-known term. HLD describes the surfactant behavior by assigning the phase transition point to be 0, or where the hydrophilic and lipophilic moieties of the surfactant or solution are at a net balance with both phases. It's interesting at this point because it's for certain surfactants, a type 3 microemulsion can form in which triple minimum surfaces are known to exist, such as the Schwarz P, known as the primitive structure, and the Schoen G, or gyroid structure, in which these minimum surfaces will form only when there is a net zero curvature. And this is somewhat the reasoning for the name of characteristic curvature, in a sense that by only utilizing known EACN oils, or oil phases that we've characterized before, we can then determine the surfactant's lipophilic interaction term, which is K, as well as the overall affinity of the surfactant, CC. The characteristic curvature of a surfactant can be thought of similarly as a HLB value, in a sense that it describes the hydrophobicity or hydrophilicity of the surfactant. Before we described HLD as a colligative model, and the reason for that is because, as you can tell on these equations above again, at no point does it ask you at which concentration of surfactant you're utilizing, nor does it ask you of anything in regards to the partitioning of the surfactant or solubility of the surfactant. In general, primary considerations is the oil phase, the concentration of your electrolyte or salinity, as well as your temperature. And as HLD stands at this state, it seems to be pretty obvious that it's a colligative equation at this point. And thus, in the next slide, we'll discuss how we can include the colligative approach to the f of a term to continue to have a colligative equation. Through my application work, we quickly recognized the large benefit to attempt to quantify numerous interfacially active solutes that we worked with day to day. And out of those, the alcohols stood out the most in the sense that they're extremely useful solvents that, when utilized in a relatively safe manner, can be readily soluble and readily soluble based on the alcoholic structure, and allows for many compatible applications. In general, aqueous solution properties are affected when adding an alcohol, and largely depends on the concentration, structure of the alcohol, and temperature, and largely temperature dependent due to hydrogen bonding. Alcohols are particular in that they are ampliphiles, and some tend to prefer to adsorb to surface sites up to around a monolayer. And ultimately, this creates a competition for solutes such as surfactants, in that they're competing for interfacial area as well as interfacial water. Alcohols themselves have been shown to lower surface tension, but they are particular in that they're not surfactants in which they cannot self-assemble by themselves. They do not have a critical micelle concentration. However, they are known to cluster and associate higher concentrations, such as one of the common points is around 10% weight by weight, in a solution in which you start to see some type of clustering with alcohols. The figure below shows a general position where anionic and nonionic microemulsions are shown, and typically, and this is just an example, is showing just typically a hexanol is known as a point at which alcohols will predominantly partition into the oil phase, while the lower molecular weight alcohols interact in the palisade layer, or particularly more with the surfactant head groups. Studies have shown that the effects of alcohols on surfactant solutions depends on the respective alkyl residue of the alcohol. Burrell and Chambou showed previously the effects of low to high molecular weight alcohols on optimum formulation positions, where it was observed to show various changes in the imply behavior as well as the solubilization. Similarly to that of specific ion effects, we saw the propanol and butanol as the break between hydrophilic and hydrophobic effects to the solution, somewhat similar to a Hofmeister effect. In general, the observations were that the solubilization of the surfactant is reduced as you increase the concentration of alcohol, and thus alcohols are commonly referred to as weak surfactants. And yet this seems to change around octanol, and those tend to be called lipophilic linkers. So, knowing this, we proposed a model using the F of A term where the concentration of the alcohol is multiplied by the normalization of the size of the solute. In this case, the molecular weight, or crudely, the molecular weight of the alcohol divided by the molecular weight of the surfactant being used. And then you would multiply this product by what we call the natural log of what we call the colligative hydration number, HC, to return back to the original salt concentration without the use of alcohol. We do want to state, however, one caveat. We do assume that there is no changes to the EACN or the oil phase when adding the alcohol. This may conflict with some previous notions that the EACN changes when you add alcohol. However, we assume that there is no changes to the excess oil phase. For the sake of time, I'm going to quickly go over the materials and the methods, but more specifically the materials. Since I gave you the handout, you can stop and look at the procedures that we showed on the left. Particularly, the two reference surfactants that we utilized in this study was sodium dihexyl sulfosuccinate, which is AMA, a common anionic reference surfactant. In our studies, we found a nonionic reference surfactant from the Novell series, 810E3.5, an alcohol ethoxylate, which could also form a type 3 microemulsion at room temperature. The alcohols that I'll be specifically talking about in this study are in bold in the table. As I discuss the results, let's start with the anionic reference surfactant, sodium dihexyl sulfosuccinate, or AMA. The first observations that were made were that there was no clear trend of the optimum solubilization parameter. In fact, of all the concentrations tested, which again were 1.5 to 6 grams per 100 milliliter of respective alcohol, there was almost no change or negligible change in the solubilization parameter, interestingly. However, there were changes in the surfactant's amphiphilic behavior observed via the changes in optimum salinities, which are plotted above against the oil phase used. Similar to Burrell and Chambou, methanol and ethanol acted hydrophilically, with ethanol acting the most hydrophilic. Propanol acted slightly hydrophilic, but remained somewhat around the same optimum salinity as the reference surfactant alone. Sec-butanol was the most hydrophobic of the low molecular weight alcohols tested, and quickly became more hydrophobic with increased concentrations. Using the optimum salinities in the oil phases, the average HLD parameters, CC and K, were extracted using the three selected concentrations of alcohol. Interestingly, CC does not seem to change, but K, philic term, does. Methanol had the highest increase in K, while ethanol had the lowest change in the characteristic curvature. Using the proposed colligative equation to model F of A and the respective alcohol concentration utilized, the experimentally found optimum salinity was used to fit the equation to return to the reference optimum salinity. This plot shows the extracted colligative numbers HC for the chosen alcoholic species, where we see the largest variance with methanol and ethanol, perhaps due to the fact that they lack a hydrophobe in comparison to the other alcohols. And using the average HC to predict the optimum salinity was also plotted next to the experimental results above, showing that the colligative approach provides a reasonable approximation. In order to determine whether the model showed repeatability, we applied the nonionic reference surfactant C810E3.5, and the same procedure was performed, utilizing the same alcohol concentrations. Unlike the anionic reference surfactant, there is a clearer trend in regards to the optimum solubilization parameter, where SP dropped or reduced as you increase the alcohol concentration. The alcohol is now acting like a weak surfactant. Again, there were changes to the surfactant's amphiphilic behavior observed via the changes in the optimum salinities, again that are plotted on the top against the oil phase used. Similar to the anionic results, methanol and ethanol acted more hydrophilically. However, ethanol is now acting the most hydrophilic in comparison to methanol in the previous case. Propanol, again, acted slightly hydrophilic, but remains somewhat around the same optimum salinity for most of the concentrations used. Butanol remained the most hydrophobic of the alcohols tested and quickly became more hydrophobic with increasing concentrations, similar to the anionic case. The optimum salinities and oil phases were again utilized to find the average HLD parameters, CC and K, and were extracted from the three concentrations utilized. Interestingly now, the K does not seem to change, but the CC, or the overall curvature of the nonionic surfactant system, is dramatically becoming more hydrophobic when the alcohol has an added alkyl. However, the lipophilic term does not seem to change, unlike we see with ethanol. This may be a result of the nonionic alcohol interactions largely affecting the solubility, as well as the alcohol influencing the behavior of the ethoxylate head group. Again, the colligative approach assumes that the interfacially active solutes interact with the surrounding water and compete with the average water molecules available. If we group the colligative hydration numbers HC extracted for both reference surfactants, the alcohol's HC values for each oil phase tested are found to demonstrate excellent agreement, as well as confirming that the additive properties of the alcohols are reappearing between the two different surfactants. The general trend of increasing the alcohol-alkyl length was observed, and shown in decreasing of the alcohol's hydration number. The highest HCs were exhibited as expected by methanol and ethanol, while 1-propanol, which had a negligible effect on the surfactant's amphiphilicity, had a HC around 1. 2-butanol had an HC below 1, indicative of the alcohol now no longer being exposed to just free water, but interacting with the surfactant within the palisade layer, increasing the hydrophobic effect. The hydrodecimic number was calculated using Zavitsas' approach with freezing point data of alcohol and water solutions from literature. Only the freezing point plots for glycerol through 1-propanol were extracted, as there was not any information on 2-butanol or 1-octanol available. The table shows qualitatively the hydration numbers extracted colligatively follow the same hydrocemic numbers in the same trend. The colligative hydration numbers were all slightly lower quantities than those found in the simple alcohol-water solutions, and this speculated that the involvement of the head groups is observed in the reduction of waters bound to the solute. So in conclusion, alcohols are useful co-solutes that with HLD can modify formulations without the use of co-surfactants or other expensive solvents. The solution behavior exhibited is mostly based on the alcohol's concentration and relates largely to the alcohol's hydrophobe length. However, we did find that the additive properties of the alcohols through the extracted hydration number showed that the alcohols are behaving similarly for both surfactant types. We found it interesting that we did not observe large changes to the solubilization parameter of the anionic surfactant with addition of alcohol, unlike the nonionic reference surfactant, and this is likely due to the affinity of the head groups towards water. The colligative hydration number values were the lowest for the anionic surfactants, and may be further evidence of non-ideality between nonionic and anionic surfactants, mostly hydrogen bonding dependent solutes. C3 may be the minimum hydrophobe length to be able to interact with the palisade layer in a type 3 phase, and this would be 1-propanol and 2-butanol. Changes in K values seem to indicate this, and thus increasing the alkyl of the alcohol will begin to induce hydrophobic behavior. Again, we also showed, not too specifically, 1-octanol behaved similarly to a linker, than that of 2-butanol. By using the additive modifications to the FA term that we proposed and accounting for their respective size and the hydration of the alcohol, the HLD returns to a colligative equation and correlates well with experimental data up to 10% short chain alcohol. And now simply, a formulator can now predict the amphiphilic behavior of other salts in interfacially active solutes using the respective additive properties through sodium chloride phase behavior scans. I would like to acknowledge the AOCS, my graduate colleague Alexis Penny, my advisors Dr. Jeffrey Harwell and Dr. Ben Chow, the Asai Glass Endowment for funding this work, and the University of Oklahoma for allowing me to do it. If you have any questions, feel free to contact me at michaelwarren@ou.edu. You can also find me on LinkedIn. Also, I'm involved with AOCS and Forum and Connect, and I will also be having a Q&A session on July 2nd.